أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم
قال رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقه قولي.
This is the dua for students for understanding and being able to explain. So first we start with a review of the older material. So basically we are trying to match binomial models to real world, and now one case is when there is a known success probability. So in that case you look at excess of successes, excess heads or too few heads, and if there is a significant deviation then you reject the null hypothesis of a good match. This is done precisely and formally by first you calculate the probability of the observed outcome under the null hypothesis. Then you form the rejection region, which consists of all events with that probability or less. Because what we plan to do is to reject for all low probability events and all except for all high probability events. And so after we look at the rejection region, we calculate the p-value, which is the probability of the rejection region under the null hypothesis. So this is also your probability of type 1 error. That is the probability of rejecting the null when it is true. And so basically we reject if the p-value is too low. And roughly speaking, in the case of heads, and in this case, it corresponds to rejecting when the difference between the observed proportion and the theoretical one, the probability, is too large. So the exact amount of how large it is, that is determined by calculating the p-value, but the general principle is like that. Now, what happens when you have an unknown p? Well, in the unknown p case, you cannot actually test for match between observed proportion and p, because the p can be adjusted to the observed proportion. So there are many different things, and we already illustrated them, and we will illustrate some more. And basically the thing is that there is no limit to the number of tests you can make, because there is no limit to the number of patterns that you can look for. And any pattern is a rejection of the null hypothesis. But the thing is that if you keep looking for lots and lots of patterns, ultimately you will find something, because even every random event will eventually have some pattern by accident. So you have to make sure that you don't plan to test too many things. At the same time, if you test too few things, then there is a chance that you might miss a mismatch. So there is a dilemma to which there is no solution. It's just a pragmatic decision. So one thing that helps is to check for stability of p, and basically that means that p remains the same. So one way to do that is to split up the sample into segments and check for the matching p in all segments. So we first set an overall p-value, and then we check each segment for match with that p-value. So then again we are back to the old test, which is reject for excess heads or too few heads. And many such cases occur that we start with something different and then it can be reduced to the same thing. So now the one thing here that is a problem is that if we have multiple tests, so you are testing many different segments, then your p-value must be adjusted, because you're not rejecting in just one case, you're rejecting in a large number of different cases. So basically your rejection region you cannot look at one separate rejection region, you have to look at all of the rejection region. So now if the rejection regions are all independent, then there is no problem, there's a easy adjustment, it's 1 minus p to the n. That's the new p-value from a combination. And as long as they are independent, you can even have different p-values in different regions, but the overall p-value will be the same. But if the tests are not independent, then you have problems. And basically today's lecture is about how to adjust p-values in the case where you cannot compute analytically the p-value. And this is the most common case. So it turns out that you can use simulations to calculate p-values in very large number of cases. And that's what we will show. So this is just a review. We can devise many new tests. Now the test should not be at random, that okay, this is something which I can think of, so let's test for that. When you are checking for a match between a theoretical model and a real world process, then your test should be guided by real world considerations, where you should think about what are the ways in which problems can arise in the real world where the model will fail to match, and then your knowledge of the real world process should be used to guide the type of test that you are going to make. So we can test for runs. This is a common test. So if you have lots of runs following each other in sequence, and then lots of failures following each other in sequence, then this kind of thing will not be detected by your proportion test, because proportion only looks at the number, it doesn't look at the sequencing. So if the sequencing is showing lots of sequences of ones followed by lots of sequences of zeros, that doesn't correspond to the hypothesis of independence and of any separation between the trials. So this can be tested separately. You can look at the number of runs you have. You can look at the largest run and ask what is the probability of this under the null hypothesis. You can look at the number of runs of 3 and so on. All of these things can be tested. You can test for higher probability. This was something we did last lecture, that is if once you have a significant deviation on the side of success, does it mean that your probability of success has gone up? And again on the other side, so then you have good periods and bad periods. In good periods the probability of success is high, in bad periods the probability of success is low. So there are various ways to check for that, and you can think of new ones. So basically the p-value method is the following. Given any event E, you can always calculate its probability by simulations. Basically what you do is you generate the same process several times, and every time you look at the process to see if the event E occurred or not. If it occurred, then you record a success 1. If it didn't occur, you record failure 0. And you look at a large number of trials, and then you look at the proportion of observed successes, and that should be equal to the probability of the event E by the law of large numbers, or approximately equal, where the error becomes small according to the standard deviation. It will be square root of p times 1 minus p over the square root of n. That is the standard error, and 2 times that will be the 95% confidence interval. So by that method you can tell how accurately, so you can tell how large to choose n so as to make your calculation by simulation reasonably close to the true theoretical probability with high probability. So the rejection reason is just one event. So we basically run the hypothesis test under the null hypothesis many times, and we look at how many times it is rejected, and that's your p-value. So it's very simple. Now I will demonstrate how this is done. So we are going to look at the same data set that we have been looking at, the Chinese dollar exchange rate, and we are looking at this process as a process of ones and zeros. 1 is an increase in the rate, and the 0 is a decrease. Increase in the rate means depreciation of the yuan. because you are getting more for the dollar. And so we ask, is this process of 1 zeros a Bernoulli process? Is every period independent, everything, or is it different? And if it is a Bernoulli process, does the probability remain the same across time, or does it change with time? So as you can see, all of these hypotheses have direct real world implications and meanings, and those are things that we need to worry about. So now, as I discussed, that we can segment the process into parts, and I discussed how we can make it into 2 parts, or we can compress it into months, 30 period, or other lengths of time. So if we divide it up into multiple segments, then we need to adjust the p-value. And of course, if multiple segments are non-overlapping, then it's possible to think that they are independent, and so you can use the adjustment formula. But now I want to look at the case where I look at all 30 period segments, contiguous ones. The first one and the first one going from 1 to 30, and the second one going from 2 to 31, and so on. So now everything is overlapping, and then there is no independence. And yet this test makes sense in the following sense that, you see, if the change occurs somewhere near the middle of the month, then it will not be easily caught, because the first 15 days will be according to one regime and the other will be according to the other regime, so it will be sort of averaged out. So you won't be able to check. So it's useful to be able to check by sliding the scale, but if you slide the scale, then you have problem with the independence. So I want to show also, this is another way to show how simulation is used. Now in this case, you see, basically the theoretical methodology for calculating the p-value would try to calculate the probability of this, and you can do this sometimes. Maybe even in this case you could do it, but you have to do very complicated analytical arguments, very difficult theory. So the simulation method is very easy because you don't need to do difficult theory. So I'm going to look at the Excel demo for this to show you how this is done. Alright, so here we have the original series. This is the yuan, how many yuans within a dollar. It's 6.5795 in the first period on February 22nd, 2011, and it went down to 6.5741, which means that the yuan appreciated against the dollar. So here we have a 0. This if statement says that if B14 is greater than B13, so is it big enough, or should I enlarge this? एक और या काफी है? ठीक है? All right, so this is the this is the if statement, which checks to see if the number has gone up. If the number has gone up, then it marks it as a 1, a success, and if it has gone down or if it remains the same, it marks it as a 0. So here we have a 0 because the rate went down, it went down again. Now it went up, so we have a 1, 0, 1, so on. So now we are thinking about what is the probability of a success. So as we saw, it's around 45%, not 50%. Actually, theory says that it should be around 50%, not 50%, it should be same. The probability of increase should be the same as probability of decrease. You should not be able to tell whether it's going to be increasing or decreasing, because if you could, then you could make a lot of money. So this is my series. That's something else. Okay. So now okay, so I don't know what happened here. Okay, so we are just going to show how this is done. Okay, so now okay, first I look at 5, 6, 7. Yes, this is the sum of all of the ones. So there are 567 ones overall, and there are 1252 periods. The last period is B1265, and B12 is it where it starts. So this is a mistake I've made. Instead of 12, I should have subtracted 11, but I subtracted 13. So it's actually 1250 is the number of periods. Let's say 11 कर दूँ, मैं इसको सही कर दूँ. चलो करते जाते हैं इसको. तो ये हो गया 1254, and so I determine the overall probability to be 557 divided by 1254, and that's equal to 452.15311. And so now I want to match, is this probability the same in every period of time? So now I'm going to look at 30 periods at a time. This doesn't have to be 30, it could be 50, it could be 20, whatever you like, and it could be all of them also. But it would have to take, we would take more time. So I want to show you how to do this for the 30 period case. So now here we have C14, the sum from C14 to C43. So that's the number of ones which occurred between period 14 and period 43, and that's exactly 30 terms in the sum. And so that's going to be some number of ones, and then what I want to do is I want to subtract the expected value, because I want to look at the deviation of this sum from the expected value. So the expected value of this sum would be the probability times 30. So if this is P star, which is 0.452, then I want to multiply that by 30, which is over here. It's C7 times 30. So now it has become 13.56459333. This is the expected value. This is how many ones you would see if 4.452 was the probability, right? So now when I look at this number, it's the third ones, and then I should look at 13.586. 9586 नहीं होना चाहिए बल्कि they should be 13.564. 5646. Okay, let me try it that way. 5646. So this will slow me down fixing the mistakes so that you might be able to follow what I am doing.
So
Okay.
expected value is equal to n times p.
क्या हुआ?
Expected value में हमने माइनस किया वो n times p करके,
हाँ 30 times.
क्योंकि हमारा ट्रायल जो है वो 0 और 1 दोनों वाली है, सेंस में ले रहे हैं इसका मीन.
Yes, the probability of 1 is 0.452 on each trial. So in 30 trials, you will get 0.452 times 30 ones, right? So that's the expected number of ones, which is 13. It's a little bit under 15, the half. It's 45% almost. 45% of 30. This is what we are getting. So that's what we would expect. So the larger the deviation that you have from this, the more you have evidence against the null. And the smaller the deviation, the more it is favorable to the null. So we're looking for large deviations in this number. So now I have 3.56 here. I'm just going to copy this down. So it goes down, and so you see you have deviation 3.56, 2.56, 1, 2, 3, 1, 2, 3. These are all normal deviations, 0. But but some of these are going to be big. Let's have a look. So far we are just seeing 1, 2, and 3. Okay, kya ho raha hai? I was trying to do a page down, I see. Now we are seeing some big deviations here, 4 and 5. 6.4, so that's a big one. Now normal deviations. Now we have huge deviation, 9.4 over one period of time. So, oops. So the max of the deviations is 9.435. Now the question is, it doesn't have to be the max, by the way. You could take the sum of all of them, or any reasonable statistic which measures the discrepancy. You need one number, and then you can test whether this is too big or too small. So now 9.4, this is a pretty big deviation, but is it too big? This is the question. So the way to answer this is to simulate the whole process under the null hypothesis. So under the null hypothesis, we have the idea that the P is 0.452875. इसने adjust कर लिया? Oh.
No sir, it is 125, it should be 1254.
125?
4.
4 होना चाहिए, okay. So now it became 0.452.
Scroll down. 1254
इसको भी वो करते हैं. Okay, so this is the probability. Now, what I am going to do is to show how the simulation works. So first what we are going to do is we are going to generate the process under the null hypothesis. So now I don't have the stock market anymore. I now have a Bernoulli process which is going to be used as a model. So now the Bernoulli process is this one. If Rand is a uniform number which takes equal probabilities between 0 and 1. So if it's less than 0.453876, which is what I had, okay, I can change that to the right number here. 452 1 5. That's enough. We don't need that much accuracy. Okay, so now if Rand is less than 452, this is 1, otherwise 0. So it's a simple Bernoulli process. This process here, this is the crucial thing about the simulation, is now, you see, the real world process we know nothing about. Whether or not it's random, whatever it is, we have no idea what it is. Now we are trying to fit a model. The model we know everything about. So I have a model, I say, okay, this uniform number is coming up with equal values. If it comes up less than 0.452, I put a 1. If it comes up bigger, I put a 0. And now I want to say, is this model matched to the real world model that I have? Now, the way I'm testing it is I'm looking at 30 period runs. So I look at the same thing. 45933 कैसे हो गया? Oh, अच्छा. Oh, this is a subtlety now. This is a subtlety, and these simulations are a little bit tricky. So now, what I do is I imagine myself in the place of the statistician. The statistician observes this sequence, and then he constructs this difference. Now, how is he constructing this difference? He looks at the sum of the 30 periods, and then from this he subtracts not 0.452. He has the average of his ones, which may be less or more at any given time. So he looks at the B3 here is this one. ये इसका enlargement खत्म हो गया. So he looks at the sum of all of the terms from A4 to A1255. Maybe wrong, but you can check it. So that's the all of the ones in the whole sequence from starting from 0 to 1200, and then he divides that by the total number of terms, which is again wrong. 1254 नहीं होना चाहिए. 1252 होना चाहिए. Okay, so now, so he will look at that, and then he will look at the deviations between this observation and the average and the 30 period average. So exactly parallel to what I did for my case, I look at the sum of the 30 periods from A4 to A33 minus 30 times the probability, and that's the deviation. I take the absolute value of that as my measure of the deviation, and now I look at the absolute value, and now I have 0.54, 0.45. So these are all the things, and it's changing here. We are getting a big value of 4, 5, 6, 7, 6, 5, 4, 2, 3, 4, 1, and so on. Now, I look at the max, which is B4, max of all of these values, and that comes out to be 8.54. So this number, 8.54, is less than 9.5. which is what we observed, 9.4. So it means that for one trial, when I did the simulation, the observed value was above. So this I record one failure, 1-0. Let me do it by hand so that we understand what's happening first. So I record a 0. I ran the simulation once, and in this simulation, the maximum observed value of the statistic was below my observed values, so I record a 0. Now the way Excel works is that whenever you make an entry in the spreadsheet, it recalculates all the random numbers. So now I have a new simulation, and it's 8.55. It's still less than 9, so I get 0. And now it recalculated, again it's 0. So what these trials are telling me is that the simulated value is pretty high. If the simulated value is normal, you find it out almost immediately. I mean, on first few trials, you immediately see that this number is within the normal range, and then you don't need to go for a very large sample. But here we are seeing that in 3 trials. Now the third trial we're getting 9.1, which is coming close. I have to go back and look at exactly what this value was. 9.43. Okay. So it's still 0. Again 0. Again 0. Oh, 9.3, still 0. But it's getting close. 8.90. Oh, now we have a bigger one. So this is the first one. So if I stop right here, I can say 3 and 3, 6 and 3, 9 and 1, 10, 11. So it's about, the chance is 1 in 11. 1 in 11 is not bad. I mean, basically not bad, meaning that the p-value is around 10% roughly. And 10% is not a rejection value. 5% or more is a rejection value. So we can say that 9.1 is a little bit high. There is some suggestion that the probability deviates, but there deviates from the probability is not entirely stable across, but the deviation is not significant, not enough to make you think that you should reject the model. So the model may be a little bit weak at some points, but not very strong. So this is what we do. But of course, this is a very small sample, and maybe we have a bad. This may not be a good estimate. So if I do it. Okay, yes, that's a question that we can answer by looking at square root of p times 1 minus p over 1 square root of n. I'll do that later, shortly. Now I want to. There is a method which is called pop tools, which can be used to simulate this 1,000, 5,000, 10,000 times. Unfortunately, I was not able to get pop tools to run on my computer because it's 64-bit and pop tools work only on 32 bits apparently. So I did another method which is in Excel, which is a little bit more difficult to handle, but it's something you can do in Excel without any additions. So this is what I did. I made a table. First of all, the table basically is a list of values. So this is value number 1, 2, 3, 4, 5, 6, so on. And this is the value. So you see this first column, this is just the sequence of numbers from 1 to 1000. This number is my simulation number. So this is simulation number 1, this is simulation number 2. At the top of the table, I have the thing which I want to calculate, and that is this C4. This is what I am calculating on every simulation. So now, what I do is in Excel, I set up a table. How do I do that? ऊपर से लेते हैं, यहाँ से ऊपर से लेते हैं. Okay. So first I highlight. So the way to do it is first I start by making my sequence 1, 2, 3, 4, 5, 6 up to 1000. If I want 1000 simulations, 500 if I want 500, 2000 if I want 2000. Generally speaking, in Excel you don't want to go much more than 1000 because Excel is very slow and clumsy in these things. So after I make, and then at the top of the second column is the thing I want to simulate. So it can be wherever it is, but there is one number that I want to keep repeating, and that is the number I put at the top. And I don't copy the number, I say equal C4 because every time it will be recomputed. Now I go into data, and I think it's in what if data table, yes. And now I don't use the row input cell because this is a column form, and in the column cell I put the top of the thing, which is either C4 or G4, I think is F4? F. Are you sure?
Yes, sir.
Acha. This is not what I think, but anyway, let's try F3. Maybe.
With Dr.
Acha. C4, okay. So now technically what's happening here is that it is giving me Yeah, what happens is, according to the table, is that it takes this 1, which is the first entry, and puts it at at the top. Ah, yes, that is the column input cell. It puts it at 1. So, in principle, oh, now I understand. Now I remember how it works. Basically, G is your function of G3, G3 is your function of F3. Normally what would happen is that I would use this value in F3 to make my calculation, and then I would come up with the result in G3, and so now this would make a whole table of values. But here I am not using the value. But the thing is that when Excel writes this value into F3, automatically it recomputes the random numbers, so automatically I get a new statistic. So here I have 1000 simulations of the G3, which, because these are going to be dynamic, so what I want to do is I want to copy these. Isko copy. Now I want to do a paste special, so as to make it non-dynamic. Okay, so now this is pasted. Now I want to sort this. Sort from largest to smallest. Okay, so it shows us that the largest in 1000 is 12, and basically what we need to do is to find where 9.4 is in this table, because that will tell us the p-value. So 9.4 is coming out here, 9.4377. It's between the 100th and the 99th value. I don't think it starts at the top, otherwise this would be about 10%. But let's see how. Where does it start?
Start from 1.
Oh, it starts at the top. So that's fine then. This goes at this goes to
10%.
10%. Yes, exactly. So the p-value is 10%, which means we cannot reject the null hypothesis. Now let's try for another way. You see, the max may not be a good reflection of what is going on in terms of, that is, maybe there is one sharp peak, but overall the process is more stable, or maybe the max is normal, but you are having a lot of high deviations and very few low deviations, so the max will not detect it. So the different types of statistics can detect different kinds of deviations. Max is good for some detecting certain types of variations, but not for other types of variations. So one thing we can do is look at the sum. They are different. Yani, you cannot say that one is better than the other. One statistic will pick up some types of things very well, and the other kind of thing will pick up other kinds of things. So we can just do it again. It's very simple. I just delete this and I say equals sum parentheses. Can I use pointing here? Yeah, I think that does it. Yeah, this goes only to 1226 because the last 30 periods are blank, remember? So because we don't have. Okay, so the sum is 2411. Oh, and everything automatically got adjusted. So it got the 2411 here, and then it created a table for this, and now I can examine what's happening here. No. Copy. Paste values. Sort. Okay, so it's pretty big, and the value here is 2567. And of course, actually, we need to look at the sum on the observations. Oh, we need to look at the original to see what happens if I sum. So replace the max by the sum. Two 810, and that's not big. 2810 is pretty small. Oh yeah, it's about yeah. So 225% p-value is very normal kind of sum. The maximum is more indicative of a problem than of the sum. Now, one thing is the process, but the real thing that you have to understand, which is the intuition behind the process. We are looking at this number, which is a statistic, which is supposed to tell us if this is a strong deviation or a mild deviation. So we just run a simulation. If it comes up all the time, then it's normal. It's not a deviation. If it doesn't come up very often, then there is something unusual about it. It's very simple, intuitive, straightforward, understandable procedure. This is something that one must learn. All right, so let's see. We have a number of other situations. Okay, yeah. So now this process can be run for anything. Now let's try together. I didn't do this at home, so let's try together to work the same principle which I did other time, where we did get a significant difference, which was look at 10 deviations above and then see if the same kind of, if there is persistence. So if we are having a lot of ones, then this will continue to happen. This is something which is not supposed to happen in a random process. So if you have even 10 ones in a row, the probability of the next item being a 1 is still 50%. So now what I am saying is, no, if you have too many ones in the past 10 period, then the probability of 1 goes up. So to test that, so now we are going to create this. So now what we are going to do is, we're going to, let me go to the next column just so I do not interfere. Now what we're going to do is, we're going to go down to about the 10th place. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now I'm going to look at the sum if parentheses sum of these 10 entries C14 to C23 is greater than. Now I want to look at the 10, 8, 9 and 10 we can consider, or we can consider 8, 9 and 10. Let's look at 8, 9 and 10. That's what we did last time. So 7.5, just to make sure that there is no confusion between 7 and... See, actually this is something that you should remember. Excel and many other math packages make small mistakes when you say greater than 7.0, because you have 7.0 and then you have 7.0 and there is a floating point error. The computer is not a perfect calculator, and it makes a small. So sometimes if you say 7 greater than 7, sometimes it will say true. 7 will be greater than 7 just by random fluctuations in calculation. So whenever you can, you should fix this so that this kind of error does not happen. It happens rarely, but when it happens, it can be very confusing because it happens only once in 1,000 times, and you're getting something which is unbelievable, and you can't track it because every time you do it, it gives you the right result. The one time in 1,000 will be very hard to catch. I've experienced with this error, so caused me a lot of frustration because I couldn't figure out what was wrong with the program. So anyway, 7.5 will avoid that problem. So if this is true, then I record a success. That means that, and otherwise I record a 0. 0. 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0
another bracket.
Oh,
Okay.
oh, some में bracket missing है. Okay, fix that. Alright, so there were not 8 ones in this period. Now I go down and I extend this to, and now how did I do this? I say take this and multiply by the next one, yeah? Yeah. So, wherever there is a 1, it means that there were 8, 9 or 10 ones in the previous period, in this period. So now what I do is, I will look at this and say equals this times, or let me do it in a different way. Okay, so I take this, which records whether or not there were 8, 9 or 10 ones, and then I multiply by the next outcome. Yes, that's right. That's all. Okay, so this will be 1 if we had 8, 9 or 10 successes, and then I also had a 1 on the 11th period, right? Otherwise it will be 0. So I can just now extend this.
It's not visible.
What? Oh, it's not visible.
Yes, sir.
So now I have, so now if I have 1, 1, that means that there was a success. So now I just want to count how many total successes there were. सम से पता चल जाएगा ना, काउंटिव से भी हो जाएगा मगर. So there were 28 periods in which we had 10, 8, 9 or 10 successes in a row. And now I want to just copy this over to the next cell. Oh. And there were only 9 periods in which there was a 1 in the 11th. So this time it doesn't show up as I had said last time. So that means that less than half, not significant, and there is not continuation of momentum. So this is not going to give us, I can test this for significance, and as I'm going to show it, but this is not going to give us a significant difference. So now this hypothesis of momentum is rejected. Maybe I made a mistake in the calculation last time because I was very surprised and I had done it in a hurry. It shouldn't happen like that, that you get a significant difference. Probably there was some Excel error that I made that led to that outcome. So here again, it shows that if somebody is looking at runs and he says, okay, now we are in the last 10 periods we have had successes, so now we are on a successful roll. So if he bets on success, he will fail actually because it's going in the opposite direction. The 28 periods that you have 8, 9 or 10 successes, you have only 9 successes on the 11th period, not even half, which would be 14. So you would actually lose money on this if you bet that, okay, after 9 successes we will still have another success. And that corresponds to the theory of efficient markets, which says that you cannot predict what's going to happen to the exchange rate. So anyway, the goal here was to show how you could test using simulations. Now almost anything that you want to, any kind of hypothesis that you want to test, any number of tests that you want to test. You see, the multiple test case is also one in which you have problems in computing the p-value. All of this can be done automatically by considering the simulation methodology. So if you are going to run 15 tests, then you have to decide, am I going to reject if any one of these tests is wrong? Then you say okay. So if any one of the tests is wrong, then rejects, then I reject. Then you have a simple statistic, which is that you look at all the tests are 0 or 1. If any one of them is 1 rejection, then you have a rejection. So you look at the sum of all the tests and you look at if it is greater than 0, then you have a rejection. That's your rejection. Now you just simulate this under the null hypothesis. This is the thing about the simulation method, that you need to know what is the distribution under the null hypothesis, but the null hypothesis tells you exactly what the distribution is. This is the thing about the null hypothesis, that you have to specify so as to simulate. Now the question as to how accurate this is an important question. For the sum, okay, there are again two methods to do that. How accurate is the p-value? All right, I show you this by another method. Okay. First, the theoretical method. In the theoretical method, this I can't use the theoretical method here right away. I can do it, but it requires a different kind of theory. If it was ones and zeros, then remember p hat was around 45%. But no, actually the p that we are trying to estimate is around 10%, because that's so in the simulation the percentile we calculated was 10% approximately. So I had a simulation size of 1000. So what is the error margin here? This is what we want to know. So basically it's square root of 0.1 times 0.9 divided by square root of 1000. That's all. That's the standard error, and I can tell you what it is. Equals SQRT of 0.9 star 0.1 slash 1000. So it's 0.01 roughly, and this is fairly stable. If you look at, let's look at that. Yeah, 0.015. So it's higher, near 0.5, but it's also that's 1%. This is 1.5%. So going from 10% to 50%, the standard error changes from 1% to 1.5%. So it's not that delicate calculation. It's not changing wildly. In some situations it changes wildly. So here 1% is what you can say is your standard error, which means that we estimated the probability was 10%. So that means that with 95% probability, the true probability that we are trying to estimate, the p-value, would be between 8% and 12%, which means that no chance of being 5%. So our simulation is okay when 1000 is giving us sufficiently good accuracy. If I used only 100, then the error would go to about 5%, and that would mean that now there is a small chance that our simulation would be misleading and the true value would be 5%, but our simulation would be telling us 10%. So with 1000 the chances are very low, 95% chance that we have hit it within 2%, and we are still quite far from the boundary. So that's how you calculate. But now I'd like to show you the other way, which is even better, and this will take care of this problem. Okay, so how I calculated the क्या था quantity उसमें 20. Oh, did I destroy that? Yeah, I destroyed it. Okay. Oh yeah, 2810. Yeah, okay. So let's go here. Now I want to find out what is the position of 2810 within this array. So that is done by looking at the percentile rank. So equals, this is a confusing concept, but it's very important. Percentile rank, कहाँ गया? Oh, अच्छा, percent rank से होता है. Percent rank. Okay, so everybody knows what rank means. Because you are all students, so you have scores. Somebody has 90, somebody has 95, somebody has 84. So the rank is position number 1, position number 2 is the second rank, and so on. So percent rank is just take the rank and divide it by the total number of students, and that's a percentage. So if somebody has rank 100%, that means he is the top. Somebody has rank 90%, that means he is in the top 90% of the students, and so on. And that's also called percentile in the SAT scores, etc. That's what you were told. So percent rank. So it says, tell me what the array is that you want to rank. This is the array. And in this, I want the rank of 2810. Okay, so this is 76%. Remember, we got it around that time, right? Now, I want to know how accurate is this 76.3%. So again, this is the great thing about simulation. This is very intuitive. Just do it again. Oh, 76.3 became 79%. Okay, now do it again.